Hey, everybody. All right, let's move on to the next topic. Next topic is we're going to talk about combustion and emissions, at least a little bit, introduction on a high level. And as I told you before, combustion has become one of the areas or disciplines within mechanical engineering, primarily because it comes up in internal combustion engines, in turbine engines, um, and in power plant design and that kind of thing. And which are all mechanical devices. So mechanical engineers tend to own this area these days. Chemical engineers are certainly involved, but it is a discipline within mechanical. So let's at least try to understand what's going on in the combustion reaction, what the emissions products are, because that's a big focus of engine design. Is you can't sell your engine if it doesn't meet the emissions requirements. And then we'll talk about what to do about the emissions and emissions after treatment. And we'll get to the point of what the current emissions after treatment technology is. So let's get started with that. So I alluded to this idea in the previous lecture. I think it was the previous lecture. Yeah, that we spray in a certain amount of fuel in order to achieve about 14.7 to 1 air fuel ratio, and we are trying to hit that number, and we are using closed loop control based on the oxygen sensor in the exhaust to control the fuel pulse width, or how long the fuel injector is open, so that if you take the mass of air that comes in, you're putting in, hopefully homogeneously mixed in there, 1 part of fuel to 14.7 parts of air. And that was the goal of the control system. So here we'll understand why, where this number comes from, or why that is. So in order for combustion to take place, you have to have the proper air-fuel ratio. So when we talk about air-fuel ratio, and what we mean by this number of like 12 to 1 or 14 to 1, we're talking about the mass of air divided by the mass of fuel. Or you could say the mass flow rate of air over mass flow rate of fuel. It doesn't really matter, but it's on a mass basis, but not a volume basis. So especially when you realize that air temperature is changing, if you drive or run your engine in a hot environment versus a cold environment, that mass may change. So the important thing is it's not a volume basis. To have, because the volume of the liquid won't change that much. It doesn't expand or contract that much, but the volume of the air does if it's hot or cold. So you have to make sure that you're doing this calculation not on a volume basis, which would throw everything off in a cold environment or a hot environment, but on a mass basis. It's specifically 14.7 to 1 is what the engines are calibrated to run with. It's possible to get combustion, gasoline combustion, maybe possible in like 6 to 1, maybe possible like 19 to 1. But typically if you go too rich, it's not going to run, and if you go too lean, it's not going to run. Think of it this way: if you have too much fuel for a given air, it's not going to burn. If you ever tried to like light up liquid gasoline, it doesn't. It tends to burn, and that's true if you take a liquid, container of gas, diesel, kerosene. Or maybe a good example would be like a kerosene lamp. If you've ever like gone camping and done a kerosene lamp, well, in its liquid form, it just burns. It burns. It doesn't combust. Okay, so what happens is if you have too much fuel in there, it's not really atomized. you have pockets of liquid in there, and it just wants to burn. It doesn't want to like combust quickly. Um, and then eventually you put so much fuel in there that it doesn't want to burn at all. It's certainly not uniformly across there. On the other hand, if you have too little fuel for the given mass, well then there are going to be pockets there where you burn up all the fuel, but there's still air left over. So you're not going to get complete combustion of all the air charge. So what you really want is, ideally what we're trying to get is, we want, the given volume of fluid or air fuel mixture that's brought into the engine. There's a given volume of that. We would ideally like a complete uniformly across there, even distribution of fuel that's atomized in that volume of air, and such that it burns through the entire thing. There's not any leftover fuel, and there's not any leftover air. If I have leftover air, I haven't got all the work out of the engine that I could have gotten. If there's leftover fuel, I have an emissions problem, because now I have raw fuel going out the exhaust. So that's where we arrive at this 14.7 to 1 number, is that ratio where all the air is burned, all the fuel is burned in all the air, and there's a complete combustion reaction across the entire volume, is 14.7 to 1. So it may, you will get operation at some range, rich or lean, but it's not going to be ideal. And then in a diesel engine, is somewhat different, because you'll recall that we're not drawing the air fuel mixture into the diesel. We're waiting until the air is high temperature, high pressure, and then we're spraying it in. So by definition, it's not homogeneous charge to begin with. You're spraying it into the hot air, and then it burns as it goes in. So it's already not homogeneous. So the 14.7 only applies to gasoline. You have a much higher fuel ratio that you deal with in a diesel engine. So and for the purposes of the combustion equations, I'm going to focus on gasoline in this discussion. Although in the after treatment, I'm going to talk about diesel. Okay, so you realize that for this thing to realize is that amount of time, like we talked about last time, you can calculate that amount of time that you need combustion to take place from when you initiate spark until you want it to be completed when there's a good lever arm on the crank. So you have this amount of time before top dead center, and then an amount of time after top dead center when you would like this done, like we talked about in that sample problem last time. That amount of time is on the order of milliseconds, especially when you're operating at high speed. So that's part of the reason that you need this atomized. You can't wait for it to just like burn over some long amount of time, and then it burns and slowly increases and whatever. You need it to actually combust quickly in order for this thing to function properly. For it to combust quickly, you need to have it, pretty well atomized in there, and uniformly atomized. So we can define this term combustion efficiency as the amount of heat input divided by the mass of the fuel times the heating value of the fuel. So what that would tell us is Q in comes from the thermodynamic stuff that we did in the first or second lecture. That's the amount of heat that we added in due to compressing the air and the air fuel mixture. Okay, that was the Q in, the heat from compressing. If we take the amount of mass of the fuel and the heating value of the fuel, that would tell us the theoretical amount of work that we could get out of it. So if we have this much fuel in there, and we know that much fuel puts off this much has this much energy in it per unit mass, you multiply that by the mass. That's like theoretically, if we got every amount of every portion of energy that's in the fuel, we turn that into work. That's the theoretical maximum. And and then if we divided to Q in over that, that would tell us how efficient our combustion operation actually is. So the goal of an engine design is to get as much work out of it as possible, or to increase the thermal efficiency. Part of increasing the thermal efficiency would be to or to get the. Remember, we had thermal efficiency, and then we said there are these reductions to get down to the actual net work produced, or the brake horsepower and the brake torque. Part of those reductions are combustion inefficiency. So, for example, if we brought in a certain amount of fuel, but some of it was left unburned, well, we're wasting that fuel, we're wasting that work potential. So theoretically, we'd want to create an engine design that got every bit of work out of the fuel that we could. That's not going to be possible, because we're at least going to lose some of the heat out of the exhaust. I mean, realize that you create this heat from combustion. You would get all the work out of the combustion if you when you open the exhaust valve, cold air went out, or at least air that's the same temperature that's the environment. But you're putting out hot air, so you know that you're getting rid of some of this potential work. There's not a lot we can do about that. There are some things we can do about that, and I think we'll talk about that next time, about this work that we're getting rid of. But another way to lose work would be to if you brought in fuel but didn't burn it, and you just put the fuel out, that would not be productive use of the fuel either. So part of that is combustion chamber design. So and if you look at your engines that you tear down, you'll see that the pistons look different. Sometimes they're just flat, but sometimes they have some contour to the surface or shape to the surface, because that's part of the combustion chamber. You will see that all the combustion chamber heads in the head where the valves are, they all look different from one engine to the other, because that's the shape of the combustion chamber, and that's going to determine how the fuel air mixture burns, how quickly it burns, whether it burns completely or leaves pockets where it's unburned, things like that. How we did that problem where we looked at, here's where it initiated, how long does it take to get to the outer edge of the chamber, how long does it take for combustion to complete fully, will it complete fully on one side but still be trying to burn on the other side, things like this. So the combustion chamber design itself is going to determine combustion efficiency, how much heat you get out of the fuel, whether you burn all the fuel. And there was a point where, let's say early 1900s, it was just kind of like, that doesn't matter so much. So long as it's burning and it's making work, who cares? Then it kind of became an engineering goal to get more output out of the engine. So let's say 50s, 60s. It's kind of like, okay, can we shape this device somewhat, control the airflow in, control how it burns inside. We may not know exactly how it burns inside, but let's empirically just try some different things and see what results in better output, better efficiency, better combustion efficiency, things like that. Then it became, when fuel economy and emissions became a real big issue in the late 1970s and 80s, then this actually became a big endeavor. Which was, how can we actually design, let's look at what's going on in there. Let's look at the fluid mechanics. Let's look at the combustion, how it takes place, and the burn rate, and what the flame propagation looks like. And that's when people started doing experimentation, looking at. I showed you that one where there was a camera inserted into the cylinder, so we could see how it burns. That is 1980s, 1990s. Um, a big part of the work there, especially as injectors came on. We want to see what the spray pattern looks like, how the spray pattern is affecting the burn rate, all these types of things. It turned into a big experimental area in the 1980s and 1990s, and continues on today. Trying to visualize, understand, simulate, test how the combustion takes place in the chamber to get better combustion efficiency and more heat out of the fuel before we send it out the exhaust valve. So let's look at the actual combustion reaction. So looking at gasoline in particular, so gasoline is actually a mixture of some different hydrocarbon compounds, mainly benzene, but then also octane. And so I want to touch briefly on this idea of of what octane means, and what that number means, because that's a common question that comes up over and over again when you go to the pump, the station pump, and they list an octane number. What does that number actually mean? So and it tends to be kind of the opposite of what people would think. If people, I think, colloquially tend to think that that octane, if you have a higher octane rating or a higher octane number, there must be like more energy in the fuel, or putting it in an engineering terms, more heating value in the fuel, like must burn hotter, must be more internal energy in the fuel, that kind of thing. It's all false. In fact, it's actually the opposite in one regard, and that is a higher octane fuel resists I guess the tendency of it to self combust. A higher octane fuel requires more energy to be put into it before it combusts, and that too is part of the reason why. I'll get into that, but let's say a lower octane fuel is more combustible. It's more volatile, such that if you use a lower octane fuel, we talked about this idea of knock. So if you take the air fuel mixture and you put it under a compression ratio of 10-1. Take a low octane fuel, put it under combustion 10-1. You don't even need the spark plug because it will auto ignite. It's more volatile. You're going to extract less work out of that fuel. It'll ignite more quickly. Being knock limited, the low octane fuel means we either need to reduce spark advance so that doesn't knock, or it would mean that we need to reduce the compression ratio. So either we're going to lose work out of it by reducing spark advance, or we're going to lose work out of it because we have to design a lower efficiency engine with a lower compression ratio. One of the two. And that's why if an engine is designed for low octane, it's going to produce more work and be less efficient. If we can modify the fuel such that it doesn't want to burn, that you actually have to put more energy into it in order to get it to combust, which is counterintuitive, because you would think that a less volatile fuel would be less desirable, that you'd get less work out of it. In fact, if we could modify the fuel such that it doesn't want to burn, it's less volatile, then what that means is we can compress it more. We can compress it more and run a higher compression ratio, or the other alternative is we could run the same compression ratio but burn it earlier. You remember we said it's going to take this amount of time to complete combustion? Well, that amount of time in a less volatile fuel will be longer. So we can start the spark advance or the ignition earlier, uh, and potentially burn that fuel longer, and we wouldn't have to worry about it knocking. Normally, we would increase spark advance to get more output, like we talked about last time, but we would hit a knock limit. But we wouldn't have to worry about it as much because this low volatility fuel doesn't want to knock. Um, so, and of course, there's a spectrum here. It's not like there's a completely volatile fuel and a completely involatile fuel. There's a spectrum here where of different octane ratings and the tendency to knock. But that's generally what's going on. So if you have an engine that has a high spark advance for performance and has a high compression ratio for either performance or efficiency, that's why you would say, well, you have to run high octane fuel in here, because we need a fuel that resists the urge to burn or self combust and create a whole knock problem, and that kind of thing. So with a higher octane fuel or an engine that's designed for a higher octane fuel, you're either going to get more performance out of it or you're going to get higher efficiency out of it, possibly both or one or the other. So there are two octane ratings out there. There's a motoring octane number, where you motor the engine and see whether or not it meaning not running. You just motor it, meaning kind of like we said that a motor is an electric motor, right? Not an engine. Put an electric motor on it and run it and without combustion and see if it knocks. And then there's a research octane number. And what you see at the pump is an average of those two, the motoring octane number and the research octane number divided by 2. And the number itself is kind of a relative number to say, is this relatively volatile and relatively likely to self-combust under compression, or is it relatively involatile and not likely to self-combust under compression? So that's what the octane rating is. It's really a tendency. How likely is this fuel to self-combust and create knock? The two things. So the one thing is the initial way to get this fuel to not knock, not self-combust, was to add lead in it. Lead makes the fuel not want to burn, right? So again, ironically, you'd think of a high octane fuel as something that has more energy and more internal energy and wants to burn. But again, really high octane fuel is one that has lead in it. The lead doesn't want to burn, doesn't burn. It's almost like an impedance to burning because we don't want it to burn on its own, or just burn under just straight combustion without a spark initiating it. So lead was the first way to do it. However, that put into the environment lead, which has all kinds of problems to it. It's a neurotoxin, and all sorts of other emissions problems with that. So lead was out of the equation. So then it became an issue of how can we adjust the composition of it. I said it's a mixture of these different hydrocarbon compounds. If we bias it one way or the other to different compounds, like ethylbenzene has a higher octane, for example. If we include more of that, it will increase the octane number and make it less likely to self-combust. So that's where it's at now. It's just different mixtures of the hydrocarbons are more likely to self-combust versus others. And so these different mixtures have different RON numbers. Okay, so let's talk about the chemical reaction now. So if we look at the actual chemical reaction, and you can drill down to every one of these specific hydrocarbons and do the reaction, but if the most basic ones, if we just look at C18H8, which is the most prevalent hydrocarbon in there. So if you take C18H8 and you do the reaction, and if you remember back to your chemistry, trying to balance the number of compounds in each side and see what you end up with what you end up with if you take the C18H8, combine it with oxygen, which is what we're trying to do in the combustion reaction, you add heat to it. What you get on the other side, if it's balanced, is you get 8 carbon dioxides and 9 water. So, and that's for one C18H8 for 12.5 O2s. So if indeed you have complete combustion and a total reaction, and you have the right amounts of fuel to the right amounts of oxygen, on the other side you should only end up with 8 CO2 and 9 water. So you'll end up with CO2 and water, and nothing other than that if you have complete combustion. So the thing is, so you say, well, it's 12.5. How do we end up with 14.7? And the thing is, so O2 is only 18% of air, and this is in. So these reactions are in moles, if I recall correctly. It's been a while since I've done chemistry also. So so this is in moles, I think, and then if we convert from moles to amount of mass, because the fuel air ratio is mass of air over mass of fuel, if we do that conversion and we recognize that air is 18% oxygen, what you actually end up with, if you talk about air to fuel mixture, you end up with 14.7 air to 1 C18H8. And that's how you get to the 14.7. That air is not completely oxygen, and you have to go from the molar basis to the mass basis. So what you end up with is this equation is actually for every 1 unit of fuel, you need 14.7 units of air. I have this written as O2, but I should say air. 14.7 air to make this completely burn. So when, again, and this is a term that goes back to your chemistry, but if you have a chemical reaction where all the reactants completely turn into all the products and there's nothing left over, that's called stoichiometric. And that's a chemical equation. That's not really a engineering it's a chemistry term, not really an engineering or a combustion term. It's just like if you have an equation that have a reaction that's completely done, there's nothing left over, it's stoichiometry. And I think the study of how to make reactions get completely done is called stoichiometry. So we would call this the stoichiometric mixture. The stoichiometric mixture is 14.7 air to 1 fuel. So and that's what we want to do. That's if things are going well for us and we're running properly, we take all the fuel products and we just get out carbon dioxide and water. That would be the ideal. That would eliminate our emissions problems mostly, and we would be using up all the fuel. We wouldn't have leftover fuel or anything else. So ideally, we almost always want to run it at 14.7 to 1. In most cases, there are some exceptions there that I may or may not get a chance to get into. There are reasons we'd want to not run 14.7 to 1. And there are engines, the more modern engines don't run at 14.7 to 1 in some parts of the operating range. For specific reasons that we don't want to run at 14.7 to 1. So I don't know if I'll get a chance to talk about that here, but let me just say as a general rule, past 30 years, vast majority of the engines out there currently, vast majority of the operating ranges are all 14.7 to 1 stoichiometric operating, which is what we want. So now let's look at the emissions issue and say, well, here, if indeed we get everything burned and it's a stoichiometric mixture, then I'm just getting out carbon dioxide and water and I won. But let's talk about what could go wrong here, or what are the other emissions that I might run into. So let's turn to the emissions issue. So what if you were slightly rich? What if instead of 1 C18H8 you put in too much fuel, or or not enough. I mean, it'd be the same thing if you had not enough air. But just for sake of simplicity, let's say that you had more fuel than one. So you had X in this equation was greater than one. Um, so instead of running 14.7 to 1, let's say you were running 14 to 1, 13 to 1, 12 to 1. That would be a rich mixture. You put in heat. What you'd get on the other side are the CO2 and the water. Excuse me, but you would also have you have extra HCs left over, and you have extra COs left over. And if you do the little balancing here, you would see that the extra C18s, H8s have to go somewhere. And where they would go is some of the carbon would combine with the oxygen, increase carbon monoxide, and some of it would not combine with anything, and you just have some kind of hydrocarbons left over, some CHs left over. So you have excess hydrocarbons, which is a problem. That is, like, what does that mean realistically? If you looked at an engine that was running rich, or the other way to think about this is incomplete combustion. Is you'll have black smoke in the exhaust products, and that black is unburned hydrocarbons, and depending on how rich it is, you'd also have carbon monoxide, which is controlled and you don't want to put into the atmosphere. So I want to point out that you also see this in another case. So you could see this in the case of where you put in too much fuel, but you'd also see this in the case of if you had a poorly designed combustion chamber. Let's suppose that part of it doesn't get burned. So let's say 95% of it gets burned, and then 5% of the mixture doesn't get burned, and in which case you have excess C18H8, excess hydrocarbons. You open the exhaust valve, and what do you have going out? You have unburned C18H8. So you can see these emissions of unburned hydrocarbons and carbon monoxide if you have a rich mixture, or if you have unburned hydrocarbons in the chamber due to either a poor combustion chamber design or too low a temperature when it burns, such that it doesn't all burn. So if you have hydrocarbon emissions, what happens is those go out the exhaust valve and out the exhaust and into the atmosphere. This is a controlled gas under the emission standards, and you can't do that. So reasons for this happening are a lot of things. Either there's something wrong with your control system such that it's not controlling to 14.7 to 1. Low engine temperature, it's operating cold, or there's something wrong with the ignition system, or something wrong with the spark plug. The gap on the spark plug is wrong potentially. Some part of the chamber is cold, due to uneven heat transfer, or the cooling around the cylinder head there's a problem there, and it's not evenly heated. It's cool somewhere. There's a cold spot in there somewhere, or maybe one of the valves are colder than the rest of the chamber. Things like that, and the result is you see it come out as black smoke, or potentially as particulates like pieces of carbon. And then carbon monoxide. Potentially, and as it gets richer, the problem gets more and more dramatic, and you could run into carbon monoxide also. And the ideal reaction puts out carbon dioxide, which is not, nowadays it's considered a really bad emissions product, and it's controlled. 10 years ago or 20 years ago, it was considered a win to not have any carbon monoxide. Carbon monoxide was the bad thing, and carbon dioxide was the good thing, because it meant that we were just getting carbon dioxide and water. So carbon monoxide is a controlled emission. Can't put out more than a certain amount of carbon monoxide, and as it gets richer, you create more and more carbon monoxide. Main reason for this is not so much the cold spot or the incomplete combustion, but it is the fuel air ratio. that you have too little air for the amount of carbon, or for the amount of fuel. So ideally, in a stoichiometric mixture, you're only getting carbon dioxide and not carbon monoxide, and that was one of the I guess kind of a joke or whatever, is that when people would get suffocated by the exhaust products in their engine or whatever, it was carbon monoxide that will suffocate you. Carbon monoxide prevents you from absorbing oxygen. Carbon dioxide doesn't really do that. So in fact, where you just have an engine that puts out carbon dioxide and water, it wouldn't really kill you so much as just maybe result in passing out from lack of oxygen. But there's no, for all practical purposes in a modern engine, there's no carbon monoxide emissions at all to kill you anymore. So let's talk about the lean mixture. So if you have the same reaction and you have less than 1 C18H8, so let's say you have too much air and not enough fuel, so that X is less than 1. What happens is when you apply the heat, especially when you have the heat of combustion and there's high heat in there, some of the oxygen is combining with all the fuel, but there's leftover oxygen. And when you have that high heat in there of combustion temperature, what's happening to the rest of the oxygen? It's going and combining with the nitrogen in the air. So what you end up on that side is the HCO2s, the 9H2Os. So you get the carbon dioxide and water, but then you also end up with this combined nitrogen oxygen compounds, which are called NOx. So and NOx, there's an X at the end because you end up with NO and NO2. NOx is a controlled emissions product, and you don't want NOx. NOx is bad for the environment. So if you were running lean, you wouldn't necessarily end up with hydrocarbons, and you wouldn't necessarily end up with carbon monoxide. If you're running lean, you would end up with NOx, which is a problem also in itself. And NOx happens in a couple cases if you're running too lean, or if the combustion is done at a really high temperature. Do you remember we talked about with the rich mixture? We said that could happen if combustion is taking place too cold. You could end up with unburned hydrocarbons and potentially carbon monoxide. If the combustion takes place too hot, which kind of sounds funny, you'd think hotter is better. If it goes too hot, you end up with NOx produced. The NOx goes out if you're running at too high a temperature, or you're running lean, too much air, not enough fuel. You'll end up putting NOx out the exhaust valve, which is a result of the oxygen, instead of binding with the hydrocarbons, the oxygen is binding with the nitrogen in the air, which happens at really high temperatures. And you can make that happen even in the absence of fuel, just if you have air that's really at that high a temperature. So you want to make sure that the combustion doesn't take place too hot, or that the cylinder head and water jacket is adequately cooled. If there's not adequate cooling in the combustion chamber, you could run into a NOx problem. Okay, so if you combine all these concepts into kind of a unified concept here, what you realize is that you're not. Well, let me put it this way: the typical engine today is designed really well. We understand how to design the chambers well. We have robust control systems such that the fuel-air ratio is controlled right. We can do CFD around the combustion chamber and the cooling to make sure that the cooling is and temperatures across the chamber are relatively uniform. It's all validated through testing to make sure that the cooling is proper and the combustion is relatively complete across the chamber. So most engines these days produce very little emissions. Just off the lot. I mean, people joke. I wouldn't do it, but people joke that if you just take a brand new car, you could breathe in the exhaust products, just like suck on the tailpipe, and and all you're getting is carbon dioxide and water out of it, which is not necessarily harmful. However, I mean, no combustion chamber is 100%. It's not burning 100% through the fuel. There's some small percentage of the fuel that's not being burned. There may be some hot spot in there that's creating NOx. There may be a cold spot that's creating CO or hydrocarbons. So it's not completely 100% one thing or the other. It's not 100% stoichiometric. It's not 100% rich or lean. You just do the best you can, and then you deal with whatever's on the other side through after treatment. So the typical engine going out of the exhaust is really well done. If you add in the after treatment that we do, by the time you get to the tailpipe, there's virtually no emissions at all whatsoever. So recognizing, however, that the chamber it's producing some of these things, you can combine these into one chart as I've shown here. And if you bias the air fuel ratio one way, you're gonna end up with more hydrocarbons and carbon monoxide. If you bias the other way with the air fuel ratio, you'll end up with less hydrocarbons and less carbon monoxide, but you'll end up with more NOx. So what everybody has decided to do is just, you can't really say that hydrocarbons are better than NOx or NOx are better than hydrocarbons. So you make the best of what you have, and you take 14.7 to 1, do the stoichiometric result, and then you take whatever you end up with in the form of hydrocarbons and carbon monoxide and NOx, and you deal with it in the after treatment. And hopefully you've done a really good job of designing the chamber, and what's coming out is minimal anyways in terms of hydrocarbons, carbon monoxide, NOx, but whatever you do end up with, you can deal with in an after treatment in the exhaust after the exhaust valve. The other thing is this is fuel air ratio 14.7 to 1. You remember that I talked about doing these spark sweeps where you change the spark advance. I also said that these emissions values were sensitive to spark advance. So maybe you would buy a spark advance for more performance, which there's a nonlinear curve there where we could hit high point of performance. Same thing with fuel economy. We might sweep and find the spot for best fuel economy. You'll also find if you plot out with spark advance, set fuel to 14.7 to 1, and then change the spark advance, 8, 10, 12, 14, 16. You'll see you can make curves of what the hydrocarbon output is, what the carbon monoxide and NOx output is. So what you might do if you end up with your final combustion chamber design, but you say, well, we need to get the hydrocarbons down or the NOx down, you could potentially bias that spark advance one way or the other to reduce the emissions. Could be at the sacrifice of performance or fuel economy, but it is an option to do. So you have that dial as well, like in your arsenal to deal with this. But recognizing that we are going to end up with this, and we're not going to get complete 100% eliminate the emissions on the other side of it. The question is what to do about it. So in terms of what to do about it, historically, the U.S. has been more preoccupied with the hydrocarbon and carbon monoxide side of things. That was the thing that they wanted to focus on, reducing unburned hydrocarbons, carbon monoxide, and people talk a lot about smog and what like that, things like that. Well, that's unburned hydrocarbons, so that could be why the U.S. focused on that. Europe, on the other hand, was focused on NOx, the NOx problem, and I'm not so much sure what the history is there, why they're so focused on NOx, um, but they are more biased towards controlling NOx versus HC and CO. They also have another problem over there, which is the local fuel has an oil or whatever has sulfur in it, and the burning of the sulfur in their fuel results in SOx. So they have that issue there, which we don't really deal with in the U.S. So which they have to deal with. So the U.S. Is more preoccupied with controlling HCs and COs. Let's talk about what we do about that, and if Europe is more focused on what to do with NOx, we'll talk about that. So let's talk about what to do. So that would be called emissions after treatment. And there are kind of three things currently that that companies do to deal with the exhaust. That's catalytic converter, NOx trap, and a particulate trap. And the particulate trap is more of a diesel thing. So I'll touch on diesel emissions as well here. So first, let's talk about the catalytic converter, which has been around for a while, and I think this is 1970s technology. When 1970s, again, you had a big push for fuel economy, but the other thing was at the same time a big push for emissions, and that was there was a big smog problem in the 1970s, or like pollution in the air, and that a lot of it was coming from cars. And if you can see it in the air, you see smoke coming out of the tailpipe. Which one is that? It's not NOx. And it's not carbon monoxide. It is unburned hydrocarbons. So that was like, what do we do about the smog problem? What do we do about the HC problem and the CO problem? That side of things. Well, you implement a catalytic converter. That was the 1970s. So catalytic converter. So it converts the so if you so if you take unburned hydrocarbons, you put CO and you put them across a catalyst. Again, this is like chemical reactions. If you put a catalyst into the chemical equation, you can make those turn into something else. And those catalyst chemicals are noble metals. They are platinum and rhodium. So essentially, you have these. What a catalytic converter is, you have this. So a flow path. Think of it like so you have a tube of the exhaust, but it the tube opens up into this block. The block has holes in it, so the air breaks into different pathways and go across this block. But the block is like impregnated on its surface with noble metals, platinum and rhodium, which catalyzes the HCs and the COs to turn into something else. And I just have this little note in here that just kind of interesting. In the 90s, Ford thought that there was going to be a run on noble metals, and emissions were going to get tighter and tighter, so they bought a ton of options on noble metals in the 90s, and they made like billions of dollars on that. But that's just kind of an aside. So let's look at what's going on in the catalytic converter. So you do have these competing interests of like if you increase the gas restriction in the exhaust, you're going to reduce the performance and efficiency and fuel economy of the engine. So how could you try to avoid that? Well, if you turn it into a much larger flow path, so you restrict it, but you kind of reduce the restriction by making it big. That would hopefully balance that out. So what you have is this. It goes through this honeycomb of different passages because you want the air to break up as much as possible and go across as much surface area as possible. And on the surface, you have these things like platinum, rhodium, palladium, these noble metals that cause the exhaust products to devolve into other compounds. So and this is the reactions. So you have carbon monoxide. So when the carbon monoxide runs over the noble metals, it's prompted to combine with whatever oxygen is present in the catalytic converter, and complete the reaction into CO2. So any CO that comes into the catalytic converter, any small amount that's left over, will react in the presence of oxygen, and then by the time it goes to the tailpipe, turn into CO2, which is not harmful like CO is. Not harmful from a human standpoint, but nowadays it is considered harmful from a greenhouse gas standpoint. But this used to be considered a big win that we're not getting any CO out anymore. And then the third one, hydrocarbons. If you have hydrocarbons going across the noble metal, it will combine with any O2 that's present there, and produce water and CO2. So the hydrocarbons aren't coming out as black smoke or hydrocarbons anymore. They are being catalyzed in the presence of palladium, platinum, and rhodium into water and carbon dioxide. So if all we had in the exhaust was excuse me, CO and HC, hopefully by the time it goes out of the chamber and into the exhaust valve, past the exhaust valve, hopefully we have very little CO and HC, and that is the case, very little. But by the time it goes through this catalyzing operation, by the time you get to the end, in fact, you don't have any HCs and COs left anymore. It's all been catalyzed in the presence of oxygen into CO2 and water, CO2 and water. So at the end of the day, all we're getting out of the tailpipe is CO2 and water. And if you go check a modern engine that's emissions controlled, so assuming it isn't some piece of lawn equipment or construction equipment, maybe that isn't controlled, but anything that's controlled will have exhaust after treatment on it, and all you're getting out of the tailpipe at this point is CO2 and water. People can breathe CO2. I don't know if I don't actually know if like motorcycles are emissions controlled. I don't know. I don't think they are. Excuse me, but that wouldn't necessarily be the case with them. But anything that is emissions controlled, you're pretty much just getting water and CO2 out of the exhaust at this point. So there, excuse me, there is this initial one here that theoretically, if NOx goes across the catalytic converter, the NOx will be catalyzed into O2 and N2. But my understanding is that the catalytic converter is not very effective at that reaction and turning NOx into N2 and NO2. So it's not. I think it can do it in very small amounts. But if your engine you're biased on the other side and you're actually producing a lot of NOx, it will not do a very good job there. Just any slight amount of NOx that incidentally tend to be in the exhaust may be taken care of by the catalytic converter, but it wasn't really the focus of the initial catalytic converter design. That was to deal with HCs and CO. So if you were really focused on the NOx problem, like they are in Europe, like we are with modern engine designs, which I'm not going to necessarily get into here. This is already kind of turned into a long video. But the modern engines, the newer engines in the last 5 years, are biased towards NOx, even in the U.S. By design. The question is, what do you do if you are NOx heavy, intentionally by design, or you're specifically sensitive to NOx like they are in Europe? What do you do about that? The catalytic converter is not going to save you in that case. The answer is you have to use a NOx trap. And you'll also hear this called lean NOx trap or selective catalytic reduction, LNT or SCR. The answer is that you if you put if you run it past the catalytic converter and then you spray urea into the exhaust products there, the introduction of the urea will like sprayed in with air and urea, spray it in, it will complete that reaction that we talked about, turning NOx into O2 and N2. and O2 and N2 are perfectly fine for the environment. So if you can complete that reaction, all you have out of the tailpipe at that point are CO2, water, nitrogen, and oxygen, and then you won. So so in fact, you'll see engines these days, or cars these days, that have a separate urea tank, and in fact, I think there's a car out there. I think it's the Mercedes out there currently. They call their diesels. I think they call them blue diesel or something like that, or blue tack or something like that. It's because there's this tank where you have to refill the urea tank, and the urea fluid is blue. That's where they get the name blue tack. So in fact, if you're running a gasoline engine specifically designed such that biased towards NOx, which again a lot of them are, you you would have this lean NOx trap and potentially the urea tank. But the other thing is diesels. Diesels also produce NOx. Diesels are producing a lot of NOx, and so one of the ways to do diesel after treatment is with the NOx trap and with the urea tank. So you'll see this on gasoline engines that are biased towards NOx. You'll also see this on diesels as part of the after treatment strategy, is a NOx trap and a urea spray. So what else do you see in diesel engines? Well, in diesel engines, you have an additional problem that we don't see so much in gasoline, and part of it's because it is a much heavier fuel than gasoline. You end up with actual particulates like smoke, small, let's say, kind of microscopic particle of carbon that, if you put it all together, you end up with smoke. And if you see a truck going down the road, it's like blowing smoke or whatever. That's what's going on. It's actually blowing. Part of it's unburned hydrocarbons, and part of it is just carbon particles in itself. But you have these actual particulates. It's not really vaporized anymore. It's actually physical particles that you can trap like with a screen or a filter kind of thing. And that's for the diesels that are really bad at putting out particulates and unburned hydrocarbons and carbon particulate. You'll have a particulate trap on the end also. And you can either just trap it there and contain it and do something with it afterwards, or you can send it back around to the intake and try to reburn those particles or those unburned hydrocarbons, burn them over again. And it's particularly a bad problem because the diesel engines, like the truck engines, the big diesels that you see going down the road, or on heavy construction equipment, that kind of thing, those are large engines in terms of displacement. So, I mean, the amount of emissions that you do is going to be, completely proportional to the amount of air flowing through the engine or the displacement of the engine. So if you have like you could have a gasoline engine that's 2 liters, but if you have a diesel engine that's 10 liters, it's going to put out 5 times as much emissions, and that's particularly bad if you have poor combustion in this diesel engine and a lot of hydrocarbon emissions and a lot of unburned hydrocarbons and unburned particulates. You don't really want that going into the atmosphere, so you trap it and then try to burn it over again, and keep doing that until you've gotten rid of most of those particulates. And then whatever's left over, you can put through a catalytic converter, or you can put through, as you see in this one here, this also has a NOx trap at the end. So you could stack these different technologies up to get rid of as much emissions as possible, and the emissions regulations set what you have to meet in order to sell your product. And the cars right now, I know, are, I'm not that familiar with the like diesel truck kind of emissions or off-road equipment. I believe that off-road equipment, like construction equipment, that those kinds of things like bulldozers, I think they don't have any regulations at all right now. And I'm not really familiar with what the emission standards are for over-the-road trucks, like semi-trucks. I don't really know that much. It doesn't seem like it must not be that stringent, because I see a lot of smoke coming out. But maybe maybe when they're new, they hit really good targets, and then over time they get worse. I don't know. Just know that cars. I know there's been so many iterations of tighter and tighter emission standards that they put out virtually zero emissions these days. In fact, that's one of the emission standards actually is well, it was partially zero emissions, and then it was PZEV, and then the goal was ZEV, which is zero emissions vehicle, which you can meet with a with a gasoline engine and the proper exhaust after treatment, where all you get out is water, carbon dioxide, potentially oxygen, potentially nitrogen. So, all right. So conclusions. That takes us through our introduction to combustion. We talked about what the combustion reaction looks like in terms of the stoichiometric reaction, what happens if you're running rich, and what happens if you're running lean, and what those reactions look like. And then we talked about the emissions implications. So, what are you getting in terms of emissions if you're rich? What are you getting if you're running lean? And then even if you're just running stoichiometric, but things aren't perfect, what are you ending up with? And then we talked about the after treatment, so that what are we doing about it? If we know there's hydrocarbons coming out or CO or NOx, what do we do about it? And the strategy is different, whether it's just a gasoline engine or it's a gasoline engine that is biased towards NOx, which a lot of the newer engines are, or diesel, which has its own problems, problems with NOx and problems with particulates. There are strategies to deal with all these things, and that's part of. It's kind of like engines or automotive companies or whatever company it is, diesel companies. They have a group doing engine design. Designing all the components that we've talked about in this class so far. The base engine components, the reciprocating stuff, the airflow components and the valve train, and designing the control system and all that. There's a group doing that. They'll actually have a different group of engineers just focus solely on the exhaust after treatment and what the strategy will be for that. So that's part of the whole effort, is not just designing the hardware, but dealing with the combustion products and what the strategy will be. So that's the combustion and emissions introduction here. So as always, make notes of questions that you have on this. Any questions that pop into your mind, let me know, and then shoot them at me, and we'll talk about it. And then we'll move on to another topic next time. So thanks for listening, everybody, and talk to you soon.